Good morning, students. Welcome to 11th Standard Chemistry video class. We are discussing Lesson 7 Thermodynamics. In our last video class, we completed up to Born-Haber cycle. In this video, we will start with the next topic, second law of thermodynamics. Second law of thermodynamics. Before starting with the topic, first let me discuss need for the second law of thermodynamics. Already we discussed zeroth law and first law of thermodynamics. Even though we are having zeroth law and first law of thermodynamics, we are in need of second law of thermodynamics. The reason is explained here. We know from the first law of thermodynamics, the energy of the universe is conserved, which means from the first law of thermodynamics, we know that the energy of the universe is constant. Let us consider the following processes. Consider the first process. A glass of hot water over time loses heat energy to the surrounding and becomes cold. Consider the second process. When you mix hydrochloric acid with sodium hydroxide, it forms sodium chloride and water with evolution of heat. In both processes, total energy remains same since they are based on first law of thermodynamics. Let us consider the first process in which heat energy is released to the surrounding and becomes cold water. If you consider reverse process of the above, the cold water absorbs heat from the surrounding, hence it does not take place spontaneously. Here, the energy change for the process remains constant since it follows first law of thermodynamics. What is spontaneous process and what is non-spontaneous process? If any process which takes place without external energy, it is said to be spontaneous process. If any process which takes place by taking external energy, it is said to be non-spontaneous process. However, if the heat energy is supplied to cold water, then it will become hot. Hence, the process is non-spontaneous. It is explained for first process. In the second process, hydrochloric acid is mixed with sodium hydroxide to form sodium chloride and water with the release of heat. If you take the reverse reaction of the above process, sodium chloride does not absorb heat energy to form hydrochloric acid and sodium hydroxide. Even though if we supply heat, the reverse reaction does not take place. Hence, there are some process which takes place in spontaneous condition and some process which takes place in non-spontaneous condition. Hence, first law of thermodynamics does not explain the spontaneity of the reaction and the feasibility of the reaction. Spontaneity means whether the reaction is spontaneous or non-spontaneous. Feasibility means whether the reaction is feasible or non-feasible. Due to the above reason, we need the second law of thermodynamics. Next, let me discuss the various statements of second law of thermodynamics. Various statements of the second law of thermodynamics. First, we will discuss entropy statement. Before starting with entropy statement, we have to know the definition for entropy. What is entropy? The second law of thermodynamics introduces another state function called entropy. Here, we are having the definition for entropy. Entropy is a measure of the molecular disorder, that is randomness of a system. But thermodynamic definition of entropy is concerned with the change in entropy that occurs as a result of a process. It is defined as ds is equal to dq reversible by T. Here we are having the definition for entropy. Entropy is a measure of the molecular disorder or randomness. Again, this entropy also defined as ds is equal to dq reversible by T. The change in entropy is given by the ratio of change in heat involved for a reversible process to its temperature, where the word entropy is formulated from second law of thermodynamics. Now we will discuss entropy statement for second law of thermodynamics. Entropy statement. The entropy of an isolated system increases during a spontaneous process. Again I repeat, the entropy of an isolated system increases during a spontaneous process, which means if any process that takes place spontaneously, then there should be increase in entropy. Here, the spontaneous process are irreversible process, non-spontaneous process are reversible process. For an irreversible process such as spontaneous expansion of a gas, delta S total is greater than 0. Delta S total is greater than delta S system plus delta S surrounding. That is, delta S total is always greater than delta S system plus delta S surrounding. Next, for reversible process such as melting of ice, delta S system is equal to minus delta S surrounding. Substitute the value in delta S total. We will get delta S total is equal to minus delta S surrounding plus delta S surrounding. Therefore, delta S total is equal to 0. Hence, we completed entropy statement. Next, let me discuss Kelvin-Planck statement. Kelvin-Planck statement. It is impossible to construct a machine that absorbs heat from a hot source and converts it completely into work by a cyclic process without transferring a part of heat to a cold sink. This statement explains that it is not possible to construct a machine which is operating in a complete cycle will absorb heat from a hot source and converts it completely into work without transferring a part of heat to a cold sink. Here, the second law of thermodynamics explains why even an ideal frictionless engine cannot convert 100% of its input heat into work, because not all the absorbed heat energies are converted into work. If all the absorbed heat energies are converted into work, it becomes 100%. Carnot, on his analysis of heat engines, found that the maximum efficiency of a heat engine which operates reversibly depends only on the two temperatures between which it is operated. It is given by the efficiency. Here, efficiency is equal to work performed by heat absorbed. Efficiency is given by neta. Neta is equal to QH modulus minus QC modulus divided by QH modulus. Here, QH is heat absorbed from the hot reservoir, where QC is heat transferred to the cold reservoir. The above equation can also be written as neta is equal to 1 minus QC modulus by QH modulus. It is given by equation 7.27. For a reversible cyclic process, delta S total is equal to delta S system plus delta S surrounding which is equal to 0. Delta S system is equal to minus delta S surrounding. Here we are having delta S is equal to Q by T. Delta S for system can be written as QH by TH. Delta S for surrounding can be written as QC by TC. Substitute the values in delta S system is equal to minus delta S surrounding. We will get QH by TH is equal to minus QC by TC. Rearrange the above equation, we will get TC by TH is equal to QC modulus by QH modulus. It is given by equation 7.28. Substituting equation 7.28 in equation 7.27, we will get neta equal to 1 minus Tc by Th. It is given by equation 7.29. Here Th is 2 greater than Tc, hence neta is less than 1. Hence we completed Kelvin-Planck statement. Next statement, efficiency in percentage. Efficiency in percentage can be expressed as efficiency in percentage is equal to 1 minus Tc by Th into 100. Again, I repeat, efficiency in percentage is equal to 1 minus Tc by Th into 100. Next, let me discuss Clausius statement. It is impossible to transfer heat from a cold reservoir to a hot reservoir without doing some work. It explains that without doing some work, it is not possible to transfer heat from a cold reservoir to a hot reservoir. Hence, we completed the topic various statements of second law of thermodynamics. It is an important detailed question. If they ask explain various statements of second law of thermodynamics, you have to give all the statements. Next topic, unit of entropy. Here entropy S is equal to Q by T. The entropy S is equal to heat energy exchanged Q divided by temperature T at which the exchange takes place. Here the unit for heat energy exchanged is given by Joule. The unit for temperature is given by Kelvin. Therefore, the SI unit of entropy is Joule Kelvin power minus 1 or J K power minus 1. Again I repeat, the SI unit of entropy is Joule Kelvin power minus 1. It is an important question. Next topic, spontaneity and randomness. Careful examination shows that in each of the processes, namely melting of ice and evaporation of water, there is an increase in randomness or disorder of the system. Consider the processes melting of ice and evaporation of water. There should be increase in randomness or increase in disorder of the system. Hence, there should be increase in entropy. In ice, the water molecules are closely packed. Hence, it allows only little movement. As the ice melts, it forms water molecules. Here, the water molecules are loosely packed. Hence, that should be free movement or the molecules moves freely in water molecules. When a water boils, it forms vapor. Here, the molecules are moves more freely than water. Hence, randomness of the water molecules increases as ice melts into water or water evaporates. Here, In both these processes, namely melting of ice and evaporation of water, they are spontaneous processes which result in increase in entropy. Consider the following diagram. Here, when a solid is converted into liquid, there should be increase in entropy. It is given by delta S greater than 0. When liquid is converted into gas, there should be increase in entropy. It should be also given by delta S greater than 0. If the process takes place reversely, the entropy decreases. It is given by delta S less than 0. Hence, we completed the topic spontaneity and randomness. Next, let me discuss standard entropy change. Standard entropy change. It is denoted by delta S naught. It is possible to calculate the actual entropy of a substance at any temperature above 0 Kelvin. Hence, the absolute entropy, which is calculated under standard condition of 298 Kelvin and 1 bar pressure, is said to be standard entropy. It is denoted by S naught. The third law of thermodynamics states, according to Nernst, that the absolute entropy of elements is 0 only at 0 Kelvin in a perfect crystal, and standard entropies of all substances at any temperature above 0 Kelvin always have positive values. Again I repeat, the absolute entropy of elements is 0 only at 0 Kelvin in a perfect crystal, and standard entropies of all substances at any temperature above 0 Kelvin always have positive values. Once we know the entropies of different substances, we can calculate the standard entropy change for chemical reaction. Here, the standard entropy change for chemical reaction is given by delta S naught R. The following expression is used to calculate the standard entropy change for a chemical reaction. It is given by delta S naught R is equal to summation of S naught of products minus summation of S naught of reactants. Again I repeat, delta S naught R is equal to summation of S naught of products minus summation of S naught of reactants. It is given by equation 7.30. Next topic, standard entropy of formation. Standard entropy of formation is defined as the entropy of formation of 1 mole of a compound from the elements under standard conditions. It is denoted as delta S naught F. We can calculate the value of entropy of a given compound from the values of S naught of elements. Here we are having the definition for standard entropy of formation. The entropy of formation of 1 mole of a compound from the elements under standard conditions is said to be standard entropy of formation. By knowing the values of S naught of elements, one can able to calculate the value of entropy of a given compound. Hence, we completed the topic standard entropy of formation. Let me stop up to this topic. The remaining topics that we will discuss in our next video class. Thank you.